Okay. So for this one, you have this sort of funky shape. And I think the origin is at the center of mass, it says. And there's a pin joint. What? Okay, let's try that again. Okay, number 5. You got this J-shaped thing. That's the origin. You have a pin joint like down here, sort of, right? And a cable up here. I think it says this angle is 45 degrees. And how long does it say the cable is? Do you remember?
It didn't, I don't think it gave one.
Right, okay. And then there's that 400 Newton force. And then can you read me off the coordinates of the different points? Okay, so let me draw this force. So you have a 400 Newton force here. And then, okay, so what do we know about these 3 points that matter, I guess? The one where the 400's applied?
That one's negative 0.5 and 0.02.
Okay. And where the pin is?
The center of mass or the one at the bottom?
The one at the bottom?
Sorry. That one is 0.05, negative 0.2.
Okay. And then the last one we need is where the cable attaches, I think?
0.6 and 0.4.
0.6 and 0.4. Okay. Okay. So a free body diagram. We have the 400 Newton force, the weight force of 20 times 9.81 is 196.2. This is a pin joint, so that's a full force vector. I'll call that R. And then there's the cable force, T. And if we make the about point the center of mass, then the coordinates of each of these points are also the row vectors so just to save a little hassle in subtracting and stuff, I'm going to do that. So my about point is going to be the center of mass, which is also the origin.
I subtracted everything to make a pin joint, the origin of
Yeah, there's a good reason to do that. What the hell? So I'll do it differently, and if we do the math the same, we'll get the same thing at the end. I mean, if we do the math right, we'll get both the same thing at the end. So 400 Newton force. The row vector is negative 0.5, 0.02. Force vector is negative 400, 0. And the cross product is positive 8. That's a Z component. And then the weight force, that's at the origin. The force is 0, negative 196.2. There's no moment. Then the pin joint, that's at 0.05, negative 0.2. Force vector is Rx, Ry. Cross product is 0.05 Ry plus 0.2 Rx. And then the cable tension. So the location of that cable tension is 0.6, 0.4. So that's the row vector because our about point is the origin. The force itself, we know the magnitude. We need a unit vector representing the direction. And in this case, since we know it's 45 degrees, we can just use cosine and sine. So, you know, if you draw the coordinate system like this, here's the vector we want. To get from the positive x-axis to the vector is just positive 45. So that's cosine and sine of 45. So that's 0.7071 t, 0.7071 t. Can someone, so cross product is this times this minus this times this. Can someone calculate that for me?
I did it using 0.71 and I got 0.085.
Okay, total 0.085 t. Okay. That seems, I mean, you know it's going to be small because it's basically just, it's 0.2 times 0.7071 t, right? Seems like it, but that doesn't look right. 0.2. 0.2 isn't? Yeah, that's what I would think there. Well, it could just be, actually, that could just be round off from rounding so much, yeah.
Yeah, because I get a different number if I use like the full.
Okay. So anyways, I'm sensitive now to the answers we get in class. I want to get them right the first time. Okay, so Newton's second law, add up all the forces and set it equal to 0. So we got negative 400, 0, 0, negative 196.2, Rx, Ry, .7071 t, 0.7071 t. And people are like, why do you use 4 digits after the decimal for cosine and sine of 45 and 3 for every other angle? Because I like to. 1, 2, 3, 4. Okay, so that's it. And then for the moment equation, we got 8 plus 0.05 Ry plus 0.2 Rx plus 0.1414 t is equal to 0. So rearrange these and you get the three equations. Rx plus 0.7071 T is equal to 400. Ry plus 0.7071 T is equal to 196.2. And the third equation says, I guess I'll rearrange a little, 0.2 Rx plus 0.05 Ry plus 0.1414 T is equal to -8. So I'll do my variables in the order Rx, Ry, T, then we got the constant. So for the first row, we have 1, 0, 0.7071, 400. For the second row, we have 0, 1, 0.7071, 196.2. For row 3, we have 0.2, 0.05, 0.1414, and -8. And that's busy. I get R is -1555, -1759, and T is 2764. I'll just call that 5. Anybody, is that what you got? Anybody get that? Okay. Any questions about that one? Yeah.
So shouldn't that 1759
I got negative. Let's see. Let's think about it for a second. Well, it looks like it should be negative because I'm just looking at the problem because you have this big force on P pulling that way that's way bigger than the 400 counteracting it. So there has to also be a, oh, well, that's the Y component, isn't it? Well, there's a big upward force.
Oh, I get it.
Okay. Yeah.
Yep, that 400. Yeah.
Any other questions? Any other problems anyone wants to see?
Well, did everybody turn in their weekly assignments? Can we see the solutions to that?
I don't have the solution with me, but I will get that graded because, there is our first test a week from Friday. So I'll get that weekly assignment graded so you can see what kind of stuff I'm gonna, basically how I'm gonna be grading this stuff, what I take points off for, that kind of stuff. Yeah, it would be nice to see the solution. I think I just did it on paper, but Yeah, I can take a picture and put it on D2L or something. Yeah.
When do we know when we have to, how do you know when we have to use the reduced rate?
You never have to use it. We could have solved this by substitution. And even on 20 equation problems, you could use substitution. But I would say once you get to 4 equations and 4 variables, this is faster, and anything more than that, it's way faster, you know. But with 3 equations, it's usually pretty reasonable, especially it would have been a bit of a hassle for me, but with your choice of about point, it would have been pretty easy by substitution. I just do it like this every time. I don't know. I tend to just, I feel like there's a benefit to just doing every problem exactly the same, whether it's 2D, 3D, whatever, you know, and it just sort of reinforces your steps, you know. The more things vary, problem to problem, the more dumb mistakes you make that you know are wrong, but you just do it out of not having habit, you know. Yeah, I think that's a good idea. When we start doing structures, we're going to have 6 is going to be the smallest number of equations we ever see, you know, so we're going to be using reduced row echelon form all the time when we get to structures. Okay. So we're done talking about, well, we finished all the stuff that you need to do those rigid body statics problems. So now I want to talk about equipolant systems. So yeah, so here we go. Equipolant systems. So an equipolant system is a system with different loads but the same behavior. So if you can replace 2 forces with a single force and a couple, for example, that is changing the loads, but you can do it in such a way that the behavior is the same. It's still in static equilibrium, or in dynamics, it still has the same acceleration or whatever. So a system with different loads, but the same behavior. So what are some examples of this? We've seen one so far. We've talked about one. And that is that you can replace a couple, which, remember, what a couple really is 2 equal and opposite forces acting at a distance. So you can always replace, I'll call it a force couple, just to be clear that that's what I'm talking about, the equal and opposite forces here, with a pure moment. And we always just do that. We never even, when we know something's a force couple, we never even write it as the 2 forces. We just write it as the moment. So this one we've already talked about. Also, you can, what's the one? You can move any force anywhere along its line of action. I'll put that in quotes and I'll tell you what that is. And it doesn't change the problem, even though you've moved the load, so it's not the same loading. This is one that is easy to do, and you might as well just always keep in mind. And then I'm going to talk about a third one too, and I'll talk about it as long as we can fit it into class today. I don't, you know, it's good to know that it's a possibility, but it doesn't really come up in problems much. And that is you can replace any combination of loads. Sort of surprising. Any combination of loads with a single force at a chosen location. Like you get to choose the location. So a single force at a chosen location. And a couple. So I'll talk about that. It's good to know it's available. There are a couple of applications where it's useful, but for the most part, it doesn't really help you that much. One thing to keep in mind. Do you have a question?
So where would they putting something, just like hanging something, putting it on the desk? Like which one does that belong to?
Yeah, I guess that's moving a force along its line of action. Because it's either or on the.
It's a 180-degree
Yeah.
flip for the.
Right.
Okay, that makes sense.
Yeah. One thing about equipolant systems is they only make sense with rigid bodies. So notice. And nothing is a rigid body, really, but it only works when you're doing rigid body analysis. If you're doing deformable body analysis, trying to calculate deformations and stresses and stuff like that, then they're not equivalent and the behavior is not the same. So it only works in rigid body analysis. So let me show you sort of why that is. Like, say you have a rigid body like this. Why did I make it so hard to draw? I'm going to copy it. Okay, so you have a rigid body like this, and there's a force applied over here. Okay. Well, this is the line of action. So you can move this force anywhere along the line of action. So you can move it to here, and the behavior is the same if it's a rigid body. But if it's deformable, if you apply that force there, you might get a deformation like that. If you move that deformation to the other side, you might get a deformation like this. So here it's the same. Here it's not the same. You follow what I mean? Okay, so moving a force along its line of action. So this picture sort of illustrates what the line of action is. It's a line that goes through the point where the force is applied, and it's parallel to the force, or in the same direction as the force stays in the same direction. So I guess let me show how you can use this in an example. So let's say that you have this guy working out giant feet. Wow. And maybe this is like the hot new exercise trend. I'm really just using that roller so that it applies the force at a point. Okay, so this is, yeah, but no, he's in static equilibrium, so he has good shoes. Nice hair. Okay, so let's say that we know that from his center of mass to his feet, that's 1/2 meter. And let's say we know that the height from the ground to where the roller hits the wall is 0.8 meters. And his feet are friction contact. What are the reactions? What are the reaction loads?
So are we treating, is there a joint where his hand needs to?
We're going to include that all as one body. So the only thing we have there is a roller. Okay, but the thing is, we don't know the height of the center of mass, right? We're not given that. Well, so we don't have to do anything because when we draw the free body diagram, the idea is the weight is up and down. And so you can move that force anywhere along its line of action, which means we can move it to the ground. We could move it to 10 feet in the air. It doesn't affect the problem. So free body diagram.
To free body diagrams is draw a picture of what you're making, but just make sure it's a little bit worse.
It is. Yeah, that's a good practice. Okay, so here's R. Let's call that RA. Here is the wall contact. I'll call that RB. That's a roller, so it has a known direction. It's perpendicular to the wall. And then here's the weight force. MG. I'm going to move these. And when we go to put numbers in this, we don't know the height, but I'm going to move that down to here, move it down to the ground. So we're going to move the weight force to the ground along the line of action. For the origin, I guess I chose his feet to be the origin. So rho, force, moment. So for the force vector RA, the rho vector is 0. The force is RAX, RAY. Well, the origin is at the feet, and so is the about point. So the moment is 0. And then the weight force, that has an x component of positive 0.5 and a y component of 0 because of where we moved it. So 0.5, 0. You with me on that? So that's where that moving along the line of action came in there. I didn't give a mass. Let's see, it looks like he had a mass of 80 kilograms. So negative 784.8. Cross product gives negative 392.4. And then the last one is the where the roller connects to the wall. And we also don't know the x component of that vector, of that row vector. But again, we can move this anywhere we want along the line of action. So we move the weight force down to here. We can move this RB force to 0x. So 0, what was that, 0.8? The force vector is negative RB 0. The cross product is positive 0.8 RB. And now you can do all those calculations. And if you did them, you would get RA is equal to 490.5, 784.8, and RB is equal to 490.5. So if you didn't notice that about moving the forces along the line of action, does that mean you couldn't do this problem? No, I mean, because the reason you can move stuff along its line of action is because it disappears from the cross products. So if I had put these in, instead of putting this weight force at 0.50, if I had put that in at 0.5 y, say, with a variable y or a variable h, look what happens when you take the cross product. You have this times this minus h times 0, and it goes away anyways. That's the reason that you can move these forces around along their line of action. Same thing with this one. If we had put this in as a w, as a variable, we would have still multiplied by 0, and we still would have gotten the same thing. Any questions about that?
Why is the RB positive?
Because my chosen direction is in the negative x direction. And so I put it into this equation as negative RB. So think of it this way. This is something that's going to confuse a lot of people later on when we get to internal loads. So think of when I draw a force with a known direction like that, think of the arrow as being a unit vector and it's being multiplied by that variable, okay? So that arrow is a unit vector in the negative x direction. So it's negative 1, 0, And we're multiplying RB times negative 1, 0. And so we come out with this expression here. Okay, so yeah, just think of those variables as the thing you're multiplying to that unit vector. It's the magnitude of the vector in that direction. Any other questions?
Should we be like on these ones with should we be putting an angle on our free body diagram if there's a known direction?
No, I don't think so. You probably have that on a drawing somewhere else. Leave your free body diagrams as uncluttered as you can. I mean, I wouldn't mark it wrong or anything, but overall, just keep those uncluttered. And if you need to draw other pictures, draw additional pictures, Okay, so now let's go to the one where, so we've done the thing of replacing a force couple with pure moment. We've done the one where you can move a force along its line of action. Now let's see that you can replace any combination of loads on a body with a load at a location that you choose and a couple. So you can replace any combination of loads with a single force at a location you choose and a couple. So off the top of your head, that strikes you as sort of surprising. So let's say this is the body, and let's say that there's an actual force. So the real force that's applied to this body is this force vector F, okay, that's applied at this point P0. And we want to, without changing the behavior of this object, treat this object like there's a force F acting at a point P, okay? Bless you. So we want to move the force F to the point P. Okay. So the way we're going to think about that is we're going to add a force couple to this. So let me copy this. Okay. And we're going to add these forces to the body. We're going to add an opposite force here, so that's a negative F vector there, and a force F here. Okay. Well, now you can see that that has the effect of moving that force F from the point P0 to the point P, so we wanted that. But is the behavior the same? It's not. We've done something, significant here. We've, by adding one force that way and one force that way, we've added a couple to this problem. That's the one thing we've changed, So we add a couple to the system. And what is the value of that couple that we've added to the system? Well, you could calculate it all in terms of row vectors and everything. We could go through that. It would be the same calculation that I did when I was talking about couples in the first place to show that they don't depend on the about point. But in that, we came up with an answer, a result, and it said that the couple that we add to the system is equal to P minus P0 all crossed with F. So by moving that force over to the point P, The only thing that we've changed is we've added that couple to the system. Okay, and so if that's the only thing we've changed, now we just have to subtract that couple to make it, you know, so that we go back to the old behavior. So we'll subtract the couple we've added. And so what you do is, so the equipolant system now has the force, this force vector F at P, and all you do is add the couple, and I'm just taking the opposite of the one that I have here. This is the one that we added before, so we want to subtract it, so we have to add this. Okay, and that's where P is the point that we want the force to be at, and P0 is where the force was originally. So let me do an example. Just like a symbolic example. I'm not going to use any numbers, but you can see sort of how this all works if you have a whole bunch of loads. Because I said you can do this with any combination of loads. So let's say that we have a force F1 at this point P1, and a force F2 at this point P2, and a force F3 at this point P3, and let's say we also have two couples, just because those can be in there too. So let's say we have a couple M1 and a couple M2. I'm drawing this in 2D, but this is all true in 3D also. And let's say that we want to express all of this whole system of loads as a single force at this point P. So if we want to express this as an equipolant system, with all the forces at P, so for the forces, that's the easy part. I mean, you just add up all those forces and that's what it's going to be. So the force at P is just going to be F1 plus F2 plus F3. Okay. And then the couple, and a couple, as long as you're dealing with rigid bodies, it doesn't matter where you apply it, it's the same. So we don't have to talk about a point where that's applied. But that couple is the original couples, M1 plus M2, and then plus P1 minus P crossed with F1. Plus the quantity P2 minus P crossed with F2. Plus the quantity P3 minus P crossed with F3. Any questions about that? One place where I've seen this before is, so like an application of this is in biomechanics. It turns out that if you're calculating, so let me draw sort of a crummy picture of the bones in your knee. Okay, and say you're trying to figure out what acceleration is going to happen from a single muscle that goes from here to here. Okay, so what happens when that muscle tightens, contracts? So if the muscle force let's call that muscle force F, and let's draw free body diagrams of the two parts of the leg. There's going to be like a contact force R, and there's going to be a muscle force F, and if you look at the lower part of the leg, there's going to be a contact force. Since these are just in contact with each other, this is going to be negative R. And this force is going to be F, and that's going to be in the opposite direction. Well, since I'm writing it as vectors, let's write it like this. And now you can, instead of treating this as a muscle force where you have to worry about where that force is applied and stuff, put both of these two forces at the contact point. So move that force F on the upper leg and that negative F on the lower leg to the contact point. Apply the two couples that you need in order to move the force to that point. And since that F and that negative F now are both on points that they both share, they cancel each other out. And all you're left with is a pure moment, equal and opposite pure moment on the upper limb and the lower limb. And it's something that you use to simplify the calculations. So let's see, these notes are not. By moving the muscle forces to the joint center, you can represent the effects of any muscle as equal and opposite couples on the two limbs. Okay, any questions? All right, so I will definitely, by Friday, make a serious effort to have those weekly assignments graded. And you should look at those and make sense out of the places where you lost points if you lose points, because those are the kind of, that's just the way I'm going to grade on exams and everything. So if you lose points on a free body diagram or something, I'll try to make notes of it, but make sure you understand what went wrong because you want to fix that for the test, okay? All right, see you Friday.